Hey everyone, welcome to 1.3 part 2. I call it misbehaving functions because these functions do not behave like the other ones in section 1.3 part 1. Here's your trivia question for today. What driver finally won the elusive Daytona 500 in 1998 on his 20th attempt? Answer later on. Okay, so misbehaving functions. Theorem 1.7. This might be a little confusing at first, but it really helps out with what we're going to be doing here the rest of section 1.3. Functions that agree at all but one point. So we've got two functions running along, and this one goes, woo, we got a little hole here, and then it keeps going. Okay, and then we have another function that goes, woo, they're all exactly the same all the way through, except for at this one point. That's what we're going to be looking at, okay? So let C be a real number, and let f of x equal g of x for all x not equal to c in an open interval containing c. So we're looking at, in this whole thing, in our interval right here, these two functions, the blue one and the purple one, are exactly the same, except for at this one little hole right there. So what we have is f and g are exactly the same except for one little spot. If the limit as g of x if the limit for g of x as x approaches c exists, then the limit of f of x also exists, and the limit as x approaches c of f of x is the same as the limit as x approaches c of g of x. So as long as one of them has a limit that goes to here, then the other one has a limit that goes to there. So it's pretty handy. Okay, so here's an example of why this all works. Alright, so let's say, example 1, find the limit as x approaches 1 of x cubed minus 1 divided by x minus 1. So if I plug in 1 in here for x, I get 1 minus 1, and I get divided by 0, and we have an error, and we have a non-distinguishable function. So that doesn't help very much. So what we want to do is we're going to try and do something to this and see if we can change this function up. So like let's say this is the f of x function, we're going to try and change it up to a different function. That way, maybe we can get rid of the x minus 1, and then we can evaluate it like we did from section 1.3 part 1. So here's the first thing. If you go in the back of your book, there is a whole list of functions. There's a whole list, not of functions, there's a whole list of formulas and other handy tips that you can use, and that was actually back there. X cubed minus 1 is actually a perfect cube. So we have x cubed minus a cubed is the same as x minus a, parentheses, x squared plus ax plus a squared. So I can rewrite x cubed minus 1 as x minus 1, parentheses. And then it's also going to be x squared plus ax, so that's 1x, plus a squared, which is 1. Alright, so that's my numerator, and then I divide that by x minus 1, and I say the limit as x approaches 1 of this. And what's nice is that x minus 1 and x minus 1 cancel out. They're no longer the same, so that means we can say this is the same. This limit, our original limit, is going to be the same as the limit as x approaches 1 of x squared plus x plus 1. Alright, you see, and now we can, from what we learned before, we can take this 1 and you can just plug it in for all those x's. So 1 squared plus 1 plus 1, and you get that to equal 3. So this is like our g function. We figured out the limit of this is 3, and if all of them are exactly the same except for at that one spot, which we removed, they are exactly the same, then I can say the limit of my original function is the same as the limit of my modified function. So, there we go. We got it. The limit of this whole thing is 3. Okay, so there's your first example. Here is some strategies for finding limits, because this is kind of what we have done before. Alright, so here's your strategy. Number 1, try to use direct substitution. Just plug it right in and see what happens. Right? That's what we did in the last section, video 1.3 part 1. If that doesn't work, let's say you get a divide by 0 error, or there's a 0 in the denominator, we have a problem. Try to cancel out so there is no divide by 0. See, that's exactly what we just did in our previous example. And then number 3, once you do that, you can use a graph or table to check your answer. Notice how it's just check your answer because AP is going to say you have to do this without a calculator, possibly. So don't rely on the calculator just to plug it in for like from section 1.2 and just plug it in and say, oh, we can just put it all in and I'm just going to look at my calculator. No, that doesn't always work. You're going to also have to do it this way. Alright, so here is example 2. The limit as x approaches negative 3 of x squared plus x minus 6 all divided by x plus 3. If I plug in negative 3 into the denominator, That's where I have a problem. Actually, if I plug this whole thing in, negative 3 squared is 9, minus 3 minus 6. This is 0 divided by 0, and that is something called an indeterminate form. We don't know if the limit exists currently. We don't know anything about it. It's indeterminate, so we have to change it up and see what happens. So I'm guessing that if I have an x plus 3 in the denominator, maybe I can factor out an x plus 3 on the top. That's really what I'm looking for. So I'm looking for x plus 3 in the numerator. Alright, so can I get x squared plus x minus 6 equal to x plus 3 times something else? There we go. Much better. X plus 3. Okay, so I know that 3 times negative 2 would be negative 6. So if I do x minus 2, let's just make sure this checks out. If I FOIL, x squared minus 2 plus 3 is plus 1. 3 times negative 2 is negative 6. Okay, there we go. So I know that this whole thing can be rewritten as a limit as x approaches negative 3 of x plus 3, x minus 2, all over x plus 3. Now I know my x plus 3's cancel out, and I'll be left with the limit as x approaches negative 3 of x minus 2, and now I can just use that direct substitution. And because these two limits are exactly the same, these two functions are exactly the same, except at that one point at negative 3, I can use this to evaluate. So negative 3 minus 2 is going to be negative 5. There we go. Okay, so there is an example of how this works. A second example. All right, now let's try a third example. Find this limit as x approaches 0 of the square root of x plus 1 minus 1 all over x. Direct substitution, 0 is in the denominator. I have a problem. So what we're going to do is, remember rationalizing the denominator? We're going to do that exact same thing. Let's just move a little bit closer here. There we go. But now we're going to, instead of rationalizing the denominator, we're going to get rid of this whole square root scenario in the numerator. So I'm going to multiply by that by x plus 1 plus 1. And if I do that on the top, got to do it on the bottom. And if you remember, now if I FOIL with this plus and minus, they're conjugates, the two middle terms are going to cancel out. So x plus 1 times x plus 1 with square roots on both of them is going to be x plus 1. And then the middle terms cancel out. Negative 1 times positive 1 is minus 1. All over, I'm just going to leave the denominator as x times the square root of x plus 1 plus 1. Plus 1 minus 1 cancel out, so I'm left with x over x times the square root of x plus 1 plus 1. And these x's cancel out. So now let's see what happens. Does this work? So if I had the limit as x approaches 0 of 1, because that's what's left in the numerator, square root of x plus 1 plus 1. So if I plug in 0, I get 0 plus 1. 0 plus 1 is 1. Square root of 1 is still 1. Plus 1 is 2. So I get 1 over 2, and I get 1/2. So we got rid of this denominator by doing something kind of creative there with rationalizing. Okay, so here is your assignment. Find the limit as x approaches negative 2 of x squared plus 7x plus 10 all over x plus 2. Good luck. Oh, before we end, let's go through your trivia question. I almost forgot. What driver finally won the elusive Daytona 500 in 1998 on his 20th attempt? The correct answer, Dale Earnhardt.